The recording has started. Good evening, everyone. Welcome to the fifth session of problem solving for the course Structural Analysis 1. Today, we'll be looking at the concept of influence line diagrams for determining the maximum internal force that could be generated in a beam due to moving loads. So, I hope the screen is visible and I've started the recording. And is my voice clear?
Yes, sir.
Yes, sir.
Yeah, thank you. So let's quickly get started. Today I will try to minimize the introductory session so that we can solve all the problems within the given time frame. So last two sessions I went too much across the scheduled time. So let me try to minimize this and spend more time on the problems. Okay, so we'll see what are influence line diagrams. So today's topic is very easy. We are not going to learn any new method of analysis. So it is not as difficult as finding the deflections or anything. You know very well how to compute the bending moments, internal force, internal shear force, and the support reactions. So we know for a given load, we have seen that so we know that for a given loading, we know how to compute internal forces. So what are the internal forces? The axial force, bending, shear force, and the bending moment. So if you are given some structure, and if you are given some loading, you know how to find out the axial force, shear force, and bending moment in all its members. But so far, we have been limited only to statically determinate structures. Hopefully, from the next week onwards, we'll be looking at statically indeterminate structures. But until now, we are looking at statically determinate structures. But in reality, the forces are not always known. For example, if there is a if this is a single story building and suppose the columns are supported in some manner, there may be people here. They can walk here and there, right? So this is called live loading, which is not, which is changing, which is not fixed. So there can be people going from here, and anywhere. So we need to find out. So for design, so we are clear with analysis of statically determinate structures. The next step is to design. For design, we need to find out the maximum values of the shear force, axial force, and the bending moment to get so that we can design. So if we design for the maximum, the lower loads will be automatically taken care. So that is the concept of today's session. We'll be considering moving loads. But be careful, moving loads doesn't mean we are not considering any dynamic effects, dynamic or inertial effects. We are doing a static analysis for a load placed at different points along the beam. So if we take a simply supported beam, if we say a load is moving in this direction, it doesn't mean that there is a load that is actually moving. That is, we are not considering the inertial effects or the dynamic effects. We are considering a load to be applied here and comparing it with the effect when the load is applied somewhere else. So static analysis of moving loads. So this static analysis of moving loads becomes very simple when we do a what is it? What to say? When we do a when we draw an influence line diagram. So what is an influence line diagram? Influence line diagram is so the influence line diagram is influence line diagram for a function. Some function, say f. This function could be a support reaction or shear force or bending moment. So what does the influence line diagram give? If we take a beam and we apply a point load at a distance x, the influence line diagram for a given function, right? Suppose I take this reaction as f, okay? Suppose we are interested in this reaction as a function of position of the point load. I want to see in which case the reaction that comes onto this support is the maximum. So what should I know? I should keep the force at different points and see where we get the maximum reaction here. So, and what is the position of the point load in our notation? Here I have denoted it as x. So the reaction, suppose I call this as A, call this as B. The influence line diagram for the beam AB for the reaction at B is By of x, where x is the position of point load. Now it is very simple in this case. So for this beam, we know if the point load is placed here, what does it mean? X equal to 0. In this case, the entire load will be taken by this support. So in this case, so when x equal to 0, Ay will be equal to 1. And By, so entire load is taken, so this takes 0. When x is somewhere in the middle, this is somewhere in the middle, that is L by 2, both will take equal, both will exert equal vertical reactions. And when x is at L, which is the right end, so the force will be somewhere here. And in this case, Ay will not take anything. The entire force will be taken by B. So if you sketch this as a function of x, that is, if you sketch By as a function of x, which is our f of x, it will be something like this. Positive 1. So this is called influence line diagram for By of this beam. So it is very simple. You don't have any new concepts. It's only a mathematical simplicity. If you know the influence line diagram, if you sketch the influence line diagram, just by looking at it, you can find out where the maximum force will occur. So if I apply 1 kilonewton, so the influence line diagram is always drawn for a unit load. Now suppose instead of 1 kilonewton, if I'm applying 10 kilonewtons, what will be the maximum support reaction coming here? So maximum By, if I apply a load of 10 kilonewtons on the beam, is how much? 10 kilonewtons. That's it. So what is the trick? If you have to find out, you have to find out to find the maximum something, okay? Maximum either support reaction or bending moment or shear force. get their ILD, which is for a unit load. And if you have a concentrated force of some other magnitude, what you should do? Multiply the value on the ILD by the force magnitude. Simple. So when we do the problems, it will become clearer. But for getting the ILD, what is the procedure? Okay, let's go through that. So for getting the ILD, so first step is to place the unit load at any general point of the beam. Okay, place the unit load at any general point on the beam, and that's all. Determine the functions of interest, whichever function we want to find out, and apply the sign convention. Simple. So this is the actual procedure, but some tricks help us to find out the IID in a simpler way. What are they? The first trick is the influence line diagram for statically determinate structures. Consists of straight line segments only. So this is a very useful trick. What does it say? If something is consisting of only straight line segments, so if you have, that is, if this, if you have to sketch the influence line diagram for some beam like this, uh, if it is in general, suppose the influence line diagram is something like this, we don't know. We need a lot of points to get this, or we should use the strict mathematical functional form and get this f of x. But if it is statically determinate, we know that it consists of straight line segments only. So what does it mean? It means that if I get the value of the function, the force function for which you are drawing the influence line diagram at specific points on the beam, then we can just connect them by straight lines. That's it. So this is a very useful trick that is helpful. But you should be careful that if there is usually if you are considering shear force, if you're considering shear force at a point, to the left and right, there will be discontinuity. At the point where we are trying to compute it. Then there will be the slope will be different for moment. So slope will be discontinuous. So this is the function itself is discontinuous. And in the case of moments, the slope will be discontinuous. For bending moment at a point. So this is just a trick to do it fast, but the correct procedure is to go through it by keeping it at a general point x on the beam. And then finding everything as a function of x. Now, what is the second trick? The second trick is also known as, it's a very, very useful trick. Before doing any computations, this helps you find the qualitative shape of the influence diagram. So what is qualitative? You don't know the values as such, but you know the shape, right? Qualitative shape of the influence line diagram. So this is also known as uh, Muller-Besnau principle. So these are the same scientists who were involved in formulating the principle of virtual work. And this trick actually follows from the principle of virtual work applied to these two systems, where one system is the actual point load, and the other system is a relaxed support. Okay, so no problem, that you can probably it would have been covered in the main lectures of the course. But the trick, what does the trick say? It says that the qualitative influence line diagram for a function is to the same scale. Wait, just a minute. To the same scale or to some scale? Let me check that. The same scale. As the deflected shape of the beam or the structure when the function, which function? This function, okay? Whichever shear force or bending moment. Let us call this function f. When the function f is acted on the beam. It's a very, very powerful trick, and this applies to both statically determinate and statically indeterminate structures. So what does it mean? Suppose I wanted, so let's take some small examples because we'll be using it in today's problem session. Suppose I want to get the influence line diagram for the reaction at A. Suppose I want ILD for reaction at A. In that case, what I should do? What does the principle say? It says that the shape of the ILD is the shape of the ILD, which is the qualitative shape of the ILD, is to the same scale as the deflected shape of this structure when F is acted on the beam. So now we have to act AY on this beam. How to apply AY onto the beam? So remove this support and apply AY here. Now how does it deflect? So there's no support and you're applying a vertical force. So it deflects something like this. It rotates as a rigid body. Which means that as per the Muller-Besnau principle, it means the influence line diagram is something like this. But we don't know what is the height. That is the only issue. We don't know what the height is. That height has to be determined by applying a unit load and seeing it. Okay. So in this reaction, we are applying an AY. So if you apply a unit load at this point, so this is the influence line diagram. So what is the maximum value? It means maximum value occurs here. It means you have to apply the unit load right here. So if you apply unit load right here, the reaction will be 1. So this is 1. And it is to the same scale. That is, if you scale x by 2 times, the y will also scale by 2 times. That is what it says. This is for a support reaction. Now, if you have to draw the influence line diagram for, say, a shear force. Suppose we take the midpoint, call this A, B, C. Suppose we want the influence line diagram for the shear force at the point C. How to do it? Now, what is our convention for shear force? If we have a beam section like this, right side downwards, left side upwards. This is the convention for shear force. And what is the convention for? So this is positive shear force and bending moment. And what is the convention for bending moment? Sagging. Right? If the beam goes like this under shear, or the beam deforms like this, this is the positive sign convention. So this is very important in all our methods, be it conjugate beam method or any method. This is very important. So as per the positive sign convention, what is the shear force? What is the direction of shear force at C? If you take a small element at C, you take a small element of the beam at C, this is the convention. So what we should do there? We should apply this shear force at C. But what is the shear force resisting? It is resisting the relative motion of the beam on left and right side of the points C. But if we have to apply C, we need to release that resistance. So what we should put is a guided roller. Right? Now we have cut out this portion. We have cut this small portion from the beam. We have cut this small portion from the beam around the point C, and we have taken it out and we are applying VC like this. But if on the left, if it is like this, what will come onto the beam? The opposite will come because internal forces have to cancel each other. So at the point A is the point B. So opposite to this should be applied on this span, opposite to this should be applied on this span. So how does it deform? This cannot move, right? Here we cannot have any motion because it is spin. So the reflected shape will be something like this. Now note the discontinuity. The deflected shape has, it's like the beam has broken and it has deformed this way, right? That is because we have supplied this. There's no longer left of C and the right of C should be the same because we have cut out the beam at the middle. So what does the influence line diagram look like? It looks something like this. How much is the value? Simple. So if the B if so the left hand limit, that is when the load is slightly to the left of the point C, what is the support reaction? It is half. Right? When we have the beam slightly to the left, or when the point load is placed somewhere here, AY will be this distance by the total distance into 1. So suppose we take this distance as x, we'll have L minus x by L into 1, which is 1 minus x by L. So at the center point, we'll have 0.5. What will be the why is the shear force 0.5? So we have an upward force of 0.5 and a downward force. When the load just moves to the right side, what will be the shear force? Okay. When the load has just crossed the point C, we don't have this -1 acting on the left span. So if you see the left span alone, it will be something like this. When the load is towards the left side, we'll have 0.5 minus 1, which is minus 0.5. When the load just jumps to the other side of C, we'll have just 0.5. So this is 0.5. This will be the influence line diagram for the shear force at the point C. Similarly, if we have a moment, say at the midpoint only. Okay, we have to find the moment at the point C. Again, cut out a small portion of the beam like this. Okay, on this, we have to apply this moment at the point C. So sagging moment is positive. And what else do we have? So once we have, if we have to apply a moment, but we should be careful that we are applying, we are applying a moment, and we should not affect the displacements at the point. So displacements have to be continuous, but we should be able to apply a moment. So replace it with an internal hinge, okay? So that you can individually apply the moment. So so equal and opposite forces you apply on this span like this. So ILD for moment at C. This is MC. How does it look like? What will be the deformed shape? You try to rotate it, how will it go? Go like this. Now what is the maximum value? That we have to see. So this is the so maximum value occurs when the load is exactly at the middle. So that is PL by 4, right? Now the load is 1. So which means the maximum value is L by 4. So this is the influence line diagram for the moment at this point C. So I hope everything is clear. In case you have any doubts, you can ask me now. We'll right away get into the problems for this week. Are there any doubts? No doubts?
No, sir.
Okay, thank you. Yeah, it is. Yeah, this is a simple concept. We don't have any new analysis methods, so you should be able to follow very easily. So let's go to the first problem. So what does the problem say? Choose the correct influence line diagram for the shear force at the point C of the following beam. Since it is the first problem, let us solve it by all three methods. What is the first method? So let us solve it by all three methods. So the first method is, we'll consider a general point X on the beam and we'll apply a unit load, which is the correct mathematical method. No shortcuts. This is the point C. This is 14. This is 6 meters. This is the point A. This is the point P. Now they're asking and this is how much? 1 kilonewtons always. Now they're asking the influence line diagram for the shear force VC as a function of X. So what is VC of X? It is always regardless of, right, okay, let me see. Suppose the load is to the left side of the point C. How much is it? It is the reaction at A minus 1 kilonewton. When the load is to the left of the point C, that is X is less than 14 meters. And when the load has crossed the point C, if you look on the left hand side, what do you have? You have only AY. So when X is greater than 14 meters. So at the point at X is equal to 14 meters, we are not really defining because the function is discontinuous. It doesn't matter what value it takes. You can have it to be left continuous or right continuous. No problem. Now let us say, what is AY? The total beam span is 14 plus 6, which is 20 meters. How do you find AY? Take moments about the point B. In that case, what do you get? AY into 20. Okay. AY into 20. So about the point B, if you take the moment, AY into 20 will be a clockwise moment. So that is equal to the counterclockwise moment, which is 1 into 20 minus X. So you will get AY into 20 is equal to 1 into 20 minus X. So this is a counterclockwise moment. This is a clockwise moment, which means AY as a function of X is 1 minus X by 20. Units, kilonewtons, because it's a force. Now substitute this in VC. Therefore, we get VC is equal to 1 minus x by 20 minus 1, which is minus x by 20 kilonewtons if x is less than 14. And it is equal to AY, which is just 1 minus x by 20 kilonewtons if x is greater than 14 meters. If you sketch the graph, you will get minus x by 20. So at 14, you should take a value of 14 by 20, which is 0.7. It's a straight line. Both are linear equations, so you'll get minus 0.7. What is the value just to the right of the point x equal to 14? It jumps by 1. So this minus x by 20, this minus x by 20 plus 1. So it jumps by 1, which is 0.3. And at the right end, what is the value? 1 minus x by 20. When x equal to 20, it is 0. So this is the influence line diagram. Well, where does it match? It matches with this. So B is the answer. So now how did we find it? We did the proper mathematical way. So this is the straightforward way. Now let us go to shortcuts. So this is the ILD for the vertical shear force at the point C. Now what is method 2? So method 2 says, method 2, using trick 1. What is the trick 1? Statically determinate beams have straight ILDs. So as I said, there will be a discontinuity as the load jumps across the point. So at this point, what is the influence line diagram value? It means the force is directly, okay, let me draw it systematically. Let me redraw the beam. So this is the point C. There's not an internal hinge. This is the point C. So if I want to find the influence line diagram for VC at this point, okay, which is x equal to 0. X equal to 0 means the load is applied at this point. And the load is applied here, what will be the shear force that comes here? And the load is applied right over the support, entire load will be taken just by the support. The beam has no role to play. So 1 minus 1 will be 0. So the point C will have 0 shear force. So the value of the influence line diagram at this point is 0. When the load is somewhere here, just to the left of the point C, okay? Say this distance is very, very small, very, very small. It is almost at the point, but it is just to the left. In that case, what will be the function value at the point C? So find out the reaction at the point A. What it is? It is 6 by 20. So the value here will be 6 by 20 minus 1. So what it is? This is 0.3 minus 1, which is minus 0.7. Just to the left, it is minus 0.7. Now, if you take the load just to the right of this point, okay? In that case, left side reaction will be this minus 1 will not come, so it will be 0.3. And when it is at the support at B, it will again have 0 shear force. So if you draw using the method 2, the ILD will come something like this. Minus this. Again, we got the same answer. Now let us use method 3, which is the shortest of all methods, using Muller-Westonhaus principle. What should we do? What does the method say? You take the beam, apply onto the beam whatever function we want to determine. So at C, replace it with a guided roller, and then you apply onto this point what you want to apply, what you want to compute, right? So apply VC here. Now, how will this deform? So this side will go down, this side will go up, it will deform something like this. These values you can determine as usual by applying a load. So that's just what we did. It is minus 0.7 and 0.3. So again, we are getting the same answer. So that is it. We have done the first problem. So so option B is the right answer. Let's go to the second problem. The maximum shear. So it's consider the same beam. Okay. Let's consider the same beam. This point A, point B, point C. The maximum shear force at the point C for uniformly distributed load of 10 kilonewton per meter of length 5 meters moves on the beam from left to right. What this means is there is a UDL like this. How much is this? They say this is 5 meters. And this UDL is moving along the beam in this direction. So as it moves, the shear force at C will keep changing. But at one point, so the shear force at C will keep changing as the UDL is moving from left to right. At one point, it will become a maximum. So intuitively, you know that when the shear force is when the applied UDL is very close to the point C, you will get maximum shear force, right? If it is closer to the supports, then the reaction will take care of the load. If it is somewhere in the middle, then the beam will bend a lot and the shear force will be more. So that is our intuition. Let us also check how to do it. Now, how do we determine the shear force at the point C? The principle here that we'll be using is principle of superposition, which we already went through a long ago. So this UDL, so UDL is acting in a rectangular block like this, in a section of the beam, and somewhere the point C is somewhere here. So from this point, right, if you take a small strip of the beam, because of the UDL, it will exert a force W into dx. Let us call this force as dF. Now the shear force at the point C, right? The shear force at the point C is summation of all such dFs. Actually, it is the summation of all the shear forces, due to such dFs. Right? If you take a small strip here, that will cause one shear force. Plus, you take a small strip next to it, that will cause a shear force like that. Now, if you tend the strip to be very small, you can replace the summation by integration. So it will be Vc due to all such df's as a function of x within the limits of the load. So let us call this point as x1 and this point as x2. So how much is Vc of this thing? It is, you will get the shear force due to a unit load at x multiplied by the intensity. What is df? df is w dx from the limits of the UDL. But what is Vc of x? Vc of x is nothing but the influence line diagram. And if you take this w out, since it is not a function of x, if you take the w out of the integral, you will get integral Vc of x dx, which is nothing but the area under the influence line diagram. So what is this trick? Now, if you have a UDL and you want to find, suppose the position of the UDL is known, if you want to find out the shear force at the point due to this UDL, draw the influence line diagram. What is the influence line diagram? There's something like this. And the shear force that is caused due to this UDL at the point C is nothing but the area under the influence line diagram within these two limits, right? So x1 is here. This is x1. This is x2. The area under the influence line diagram between the 2 points of the UDL is equal to the shear force. Now, what are they asking? They're asking us to find out the maximum shear force at the point C. So with your judgment, you know which location of, so this is minus and this is plus. So where should I place the UDL so that I get maximum area under the curve? Any guess? If I place it here, right? If I place it here, the corresponding area from will be from here to here, which is very, very small. As I move to the right, here I have a big trapezium. So you may feel that the shear force, the UDL has to be placed somewhere here. What happens if I cross this point? Say if I keep the UDL somewhere in between, both in the positive and negative ILD areas. What will happen? If I keep it somewhere like this is negative, this is positive. So some portion of this will be cancelled by this. So that's actually a not correct position to place the UDL. Again, if I keep it too much to the right side, it will be useless because again, this area will be very small compared to anywhere in between. So based on this inspection, we find that the best place to keep the UDL to get maximum shear force is here. Because this is the maximum area we can get. Because if the UDL span is fixed, so this is 5 meters, that is fixed. So this is the maximum area we can get. If it crosses this, it will cancel out with the positive. If it goes below, it will be less. Now what? Let us find out what this is. Okay, so this is 0.7. So here it is minus 0.7. Here what will be the value? This total is 14. So this will be 9. So here the value will be 9 by 14 into 0.7, which is nothing but 0.45. What is so now let us find out the area under the curve. So area under the curve will be, it's a trapezium. So area of trapezium is half b1 plus b2 into height. So here base 1 is 0.45 plus 0.7 into height is 5 and there's a minus 1. Now area under the curve is, okay, this is the area, but this is for a unit load. But what is the actual load? It is multiplied by W. And how much is the given W? 10 kilonewtons per meter into 10. So if you, yeah. Now if you write down with proper units, you will get half into 0.45 plus 0.7 is 0.115 meters. Sorry, yeah, it's in meters. So it is kilonewtons per kilonewton. It's not meters. Its shear force is in kilonewtons for a unit load by 1 kilonewton to 5 meters into 10 kilonewtons per meter. So if you compute, the units will be kilonewton, kilonewton gets cancelled, meter, meter gets cancelled. You'll get kilonewton, which is the shear force. If you find this, the answer you get will be, I've solved it, so it will be 28.75. Which direction? Negative, right? It means the shear force at that point is, you take, it's upwards on the left side and downwards on the right side. So what is the answer? 28.75. So option A is the right answer. So this slightly involved problem, if you have a UDL, you should see where if you place the UDL, you will get maximum area. And then find out the maximum area, that is the maximum shear force at the point C. Now let's go to the next problem. So here we have a yeah. Just a minute. Yeah. Now this is a simple problem. We'll see. So let us choose the correct influence line diagram for the shear force at the point D of the following beam. So you can use any of the methods, but since they're asking only the we can use any of the methods. So let us start with the method 3, which is MB principle. You'll see how powerful it is. So at the point D, we are interested in the shear force. So cut out a small portion from point D, apply the positive direction shear force. This is the point D. This is VD, VD. In the actual beam, what you should do, since you have cut out a portion, put a roller because the rotation shouldn't be released, but the relative displacement should be released. Here, what do you have? Here you have a hinge. Here, what do you have? Here you have the support. Here we are applying this force. VD. This is the point C. This is the point B. This is the point A. When we apply this force, you see here it's a cantilever beam. You should be very careful. It doesn't mean this beam will bend in this way. No, that's not correct. Why? It's a relative force, relative slip between the two that we are applying. Between the two sides of the small beam section, we have to apply a shear force. So we are not applying a displacement, we are applying a shear force. So will it move? This side is a rigid body mechanism. This side, it is a deformable structure. So when you have a rigid body mechanism, this will only rotate and form some shape. This will not move because to move this, you need to apply some force. If it has to deform, then it has to get some energy. So that is not that will not happen. If this is possible, that will not happen. So the deformed shape will look something like this. Will not move at all. But with respect to this has to go up. So the beam is not and the rotation is not allowed here. So here it will be something like this. Now this joint is free to rotate. So do you think it will move up or down? No, it will be this joint is free to rotate. So and this maintains 90 degrees. So it will be like this. And since it is free to rotate, the slope onto the left and right can be different. So the deflected shape will be something like this, which means the ILT will be like this. So it looks like 1 is the answer. Let us also verify by the other method. How to do it? Simple. So as usual, let us apply a point load to the left side of the point D. In any case, so when the load is, so what we are interested in is VD. VD is equal to, left side we have moments and so many other things. So let us look at the right side of the beam. So VD is equal to RB. So when the load is to the left side of the point D, there's no other load on the right side. So it's just equal to RB when X is less than or equal to 8 meters. X is the point where the load is applied. And in the other case, it is RB minus 1 when X is greater than 8 meters. What is RB? That we have to do an actual analysis. So when the force is to the left of this point, how does it look? This is the point D. This is X. This is case A. This is X. Here you have an internal hinge. And here you have the support. The internal hinge cannot take any moment. So if you do sigma MC equal to 0 on this structure, you will get RB is equal to 0, which means VD of X is equal to 0 if X is less than or equal to 8 meters. Now suppose you take X is greater than 8 meters, right? X is greater than 8 meters, but it is less than, it is in the span D to C. So suppose you take the second X here, you apply the force here. It has not crossed C and it is before the point it has crossed D, but it has not crossed D, crossed C. In that case, what happens? Again, sigma MC equal to 0 if you apply. What will you get? You will get RB as 0 because there is no loading in this span. If you take moments about this point, you get RB into some A8 equal to 0, which is 0. But since the load has crossed the point D, you should use this formula for finding the shear force. So I'll get 0 minus 1 is 1 minute. I think there's a sign mistake. RB upwards is actually negative shear force, right? As per our convention, this is our positive sign convention. So it's actually minus of this. Okay. So here, sorry for this. So RB is 0. So 0 minus 1 is 1. 0 minus 1 is minus 1. Minus 1 into minus 1 is plus 1. So when X is greater than 8 meters and X is less than or equal to 4 meters. In that case, it's a constant. So that is fine. Then when the load crosses this as well, in the third case, let us consider the load has crossed C also. So this is X and the load is somewhere here. In that case, what will be RB? Then in that case, RB will be, we have to find out. So if you take moments about the point C, you get RB into 8 meters is equal to, what is the moment due to this? So this will create a counterclockwise, this will create a clockwise moment. 1 into X minus 12. Okay. So we will get RB is equal to yeah, you will get RB is equal to X minus 4 by 3. Sorry, 3 by 2. X by 8 minus 3 by 2. So here in this case, so what is B of D? It is minus 1. So I'll get, and there's a minus overall. So I'll get minus X by 8 plus 5 by 2 when X is greater than 12 meters. So if you substitute in this, to substitute the values in this, you will see that at X equal to 12 meters, you get minus 12 by minus 3 by 2 plus 5 by 2, which is 1. So at the point X equal to 12 meters, it is continuous. And beyond that point, when X finally reaches 12 plus 8 is 20. 20 by 8 is 5 by 2, it is 0. So if you sketch the value, it will look, if you sketch the influence line diagram, from X equal to 0 to 8, it is 0. From 8 to 4, it is a constant. And at 12, it is 0. And it is continuous here. So it looks like this. And what is this value? It is 1. And what is this value? It is 1. So that is what we have got here using the Muller-Breslau principle. So the correct answer is A. Let's go to the next question. They're asking the maximum bending moment at the point D of the beam shown in question 3. So this is the same beam. Let me redraw it here. So it's like this. Instead of the shear force at the point D, this is D, this is C, this is B, this is A. Instead of a shear force, they are asking the bending moment. So if you have to apply a bending moment, what you should release? You should release the rotation. You should not release the displacements. So left side and right side can have a different slope, but not different displacements. So in that case, using Muller-Breslau principle, in which direction you should apply a moment? On the point D. If you take a small segment of the beam at the point D, there is moment like this. So here on the beam, on the remaining portion, it should be equal and opposite. MD. Now how does the beam deform? Be careful, now it cannot slip. So, and what will happen? As I said in the last time, you're applying this at a point. So it's very close to each other. It's not that you are doing it independently. At that point, you're bending the beam with a moment of MD. So what happens? The left side will not deform because it is sufficiently supported. You have a cantilever. It will not deform. Since the right side is having a rigid body mechanism, left side will not deform. So if you draw the deformed shape of this, it will look something like this will not deform, but here it can generate a rotation because it's a spring. It's a hinge. Again, here you have another hinge, but here the displacement have to be zero since it is supported. But the rotation can be non-zero. So this will be the deformed shape once you have applied MD. So by Muller-Boslov principle, you can say the bending moment is something like this. Negative. Now that is fine. So this is MD. What are the magnitudes? Okay. So this is the ILD. This is not the BMD. This is the ILD for moment at the point D. Now what will be the maximum value here? Let us find out. Let us apply. So this is the point C. At the point C, we have to apply a unit load to find out the maximum value at D. So let us analyze this beam. Very simple. So you have an internal hinge and you have a concentrated force coming onto the internal hinge. How do you analyze this? So let us take moments about this point MC, right? If you consider the right span and take moments about this point, you will get RB equal to 0. So on the hinge, this beam is connecting RB equal to 0, which means this side there's no force, and this side there is some other force. On the hinge, the shear force that comes is something like this. And in addition to that, you have the applied force of 1 kilonewton here. So this force is equal to 0, which means this force is equal to 1 kilonewtons. So if you consider the left side part of the beam, this is the point D, you have a bending moment MD, you have a shear force VD, right or up or down, it's up. So this is VD. And here you have an upward force on this, which means here it is downwards. On the hinge, it is upward, so on the beam, it is downwards, which is 1 kilonewtons. So what is MD? VD is equal to 1 kilonewtons and MD is equal to minus 1 into this much. How much is this? I think 4 meters. Yeah, 4 meters. So this is 4 meters. So this value is minus 4 kilonewton meter for 1 kilonewton load. That you should be clear. That is done. Now what is the question? They're asking that live load of 5 kilonewton per meter distributed live load is acting, but the span of the live load is longer than the beam. So if this is the beam, you have a live load something like this. And the live load is moving somehow. So if it is moving and its span is longer than the beam itself, when will you get the maximum moment? As I said, we have a UDL. So UDL means the moment at a point is equal to the area under the influence line diagram for the moment at the point between the limits of the uh, distributed load. So here, if the live load is acting everywhere in the beam, this entire area will be covered. But if the live load is acting somewhere, if the live load has already left half of the beam like this, then only so much area will come. But we want to find out the maximum. So maximum moment will occur when the live load is everywhere in the beam, or at least over this portion. So when it is fully over that portion, what is the maximum area? So half, it is the area of the triangle. It is half into what is base? Base is 8 plus 4. meters into height is -4 kilonewton meter per kilonewtons into this is the area of the ILD into what is the force intensity, the distributed load intensity, 5 kilonewtons per meter. So the units will be consistent. Kilonewton gets cancelled. So you will get 8 plus 4, 12, 12 by 2, 6, 6 4s are 24, 24 5s are 120. And it is hogging, right? It's negative, so it is hogging. We assume sagging to be positive, but we are getting hogging. So the correct answer is C. Let's go to the next question. Now choose the correct influence line diagram for the following beam. Note in each diagram for which the ILD is drawn, it is mentioned. So the first one is for the reaction at B. Second one is the ILD for the reaction at A. Third one is the ILD for the bending moment at D. Fourth one is the ILD for the shear force at C. Let us do each of these individually. So let us look at option A. Is it correct or wrong? So option A, ILD for the vertical reaction at B. Now what we should do? This is the beam. Let us use the MB principle because now we know it is very simple to analyze it that way. So at B, we have to find the reaction, which means you apply the reaction there. So remove the support and apply the reaction By. Now what will happen? This is an internal hinge, so it can accommodate relative rotation. So the deflected shape will be something like this. Correct? If you have, this is the point A, D, C, and B. So the deflected shape will be something like this. So if you draw the ILD for the reaction at B, it will be something like this. And what will be the maximum value? Maximum value is when the unit load is right above the point B, which is 1. But the point C is somewhere here. This is starting at D. So this is wrong. Let us look at option B. They are saying this is the influence line diagram for the vertical reaction at A. Now at A, we have to release the vertical support and apply the vertical reaction of AY. And the rest, let us just redraw. Something like this. Now, if you apply a vertical support, a vertical reaction here, it is like a seesaw. So it is this is like a fulcrum point. This is moving up, and there's an internal hinge here. So how will it deform? If you see, this will remain straight. It will remain straight. Since it is a hinge, it can accommodate relative rotation. It will go like this. So if you see the vertical, if you draw the vertical ILD for vertical reaction at A, it should look something like this. And this maximum will be 1 minus. So, but what they have given, it has to go like this. So this is also wrong. Now, if we see the option C, we have this. We have an intermediate support. And this. They're asking the bending moment at point D. That is the bending moment at this point. So to find the bending moment at this point, ILD for the bending moment at this point, what we should do? We need to apply the bending moment here. So release the continuity of the beam here. So the slope can be different on both sides. So you have to apply this. You apply a sagging bending moment on both sides of the beam like this. Then what will happen? Is there an intermediate support? Yeah, there's an intermediate support. So But you have to retain the vertical this thing. So it means you're putting an internal hinge, but you're not releasing the vertical restraint. So left side will not deform. It will remain like this. So left side will remain like this. Right side will go like this. Since it's an internal hinge, it can take. So the bending moment in this case will be like this. ILD for the bending moment will be like this. Maximum value we can find out whatever it is, right? So maximum value occurs when it is at this point. So what is the value? It will be, I think, so here if you apply unit load 1, what is the bending moment at the point D? I will do it. Okay, anyway, I will show it. So to get the maximum bending moment, this is 4. Here we have an internal hinge. Right side, it cannot take any force. Why? Because there cannot be any moment here. If there is a force, then there should be a moment here. So right side, it cannot take any force. The entire applied 1 kilonewton comes onto this span. So onto this span, we have 1 kilonewton. This is 4 meters. So we need to find the bending moment at this point. Sorry, at this point, D. Right? So how much is it? 1 acting at 2 meters. So this maximum value is 2 kilonewton meters per kilonewton. Again, it is not matching, so this is also wrong. So obviously the answer should be option D, but let us do it. Shear force at the point C. So at the point C, we have already a internal hinge. Now, in addition to the internal hinge, we should also release the relative displacements. So at this point, we already have an internal hinge, but in addition to it, we'll also release the relative displacements like this. And what is the direction? Like this. Will the left side part deform at all? No, because it's a relative shear that we are applying. So something like this will happen in the intermediate. So left will remain as it is, this will go up. So deformed shape will be something like this. VC. So the ILD is how much? 1. So this is the right answer. Option D is the right answer. So we are halfway through today's session. Let me pause if there are any doubts and then I can go ahead. Any doubts? Okay, let me go ahead. I assume there are no doubts. We'll go to problem 6. Now they're asking the maximum bending moment at point D of the beam shown in question number 5. So let's go to the previous page and let me copy the ILD for the maximum bending moment, ILD for the bending moment. Okay. So this is the question. So this is the beam. Okay, I'm unable to select it, but so let me just take the ILD for the maximum bending moment. Okay. This copy it here. So this is the influence line diagram for the maximum bending moment at the point D. As usual, they have said that the span of the load is longer than the span of the beam, which means the beam is something like this. And the load extends much longer than this. So obviously we know from our intuition that when the entire beam is loaded, we'll have more bending moment than when a part of the beam is loaded. So when the entire beam is loaded, this this entire area will contribute to the maximum bending moment. So what is the maximum bending moment at the point D? It is the area of this triangle. So half into how much is the base of the triangle? This is 2. This let me read. This is 2 meters, 2 meters. This is 4 meters. Yeah. So half into base. Base is 4 meters into height. Height is 2 kilonewton per for 1 kilonewton load. And what is the load intensity? Force intensity is 20 kilonewton per meter. Now check the units, it should be correct. Meter, meter, meter. So we'll get 1 meter and kilonewton. So we'll get 2 into 2, 80. Is it sagging or hogging? It is hogging. This is the point D. So you will get option B. So you get option B. Now let's go to problem 7. We have a wheel load of 20 kilonewton, which is moving on the following beam from left to right. What is the maximum shear force at a point E, which is located at 3 meters to the right of this support? So let us mark the point E first. And this is 3 meters. This is 2 meters. Now, they're saying a wheel load of 20 kilonewton is moving. So first step, as always, is to get the influence line diagram. How do we get it? As usual, let us release the shear resistance at this point. Right? There's a shear force here. Let us release it and apply the shear force. So left span down is positive, right span up is positive. So if you apply this, we'll get, you see it's again like a seesaw. It is supported at one point. How will it deform? It will go down like this, right? And on this span, it will go like this. So the center line is somewhere like this. This is 2 meters, 3 meters, 2 meters, 2 meters. So let me draw it to scale. So the influence line diagram will look like this is 2 meters, this is 3 meters, this is 2 meters and 2 meters. So influence line diagram will look something like this. Note that wherever we have a support, right? Wherever we have a support, we have zero influence on the shear force at the point C. Why is that? It means that when the force is applied directly over the support, the beam is not having any role to play. So the VC will be zero. This is positive, this is negative, this is positive, this is negative. Let us find out the magnitudes, okay? So what is the value at this point? It is nothing but when the beam is loaded here. It's 5, 2, 2, 3. So when we apply a force of 1 kilonewton here, what will be the shear force? Let us do it. let's take moments about the point C equal to 0. We'll get -1 kilonewton into 5 plus 2, which is 7. It's clockwise, counterclockwise, right? So plus 1 kilonewton into 7 meters minus dy into 5 meters is equal to 0. So we get dy as 7/5 kilonewtons per 1 kilonewton. So, and what is Vc? Vc is always, not always, Vc is dy minus 1 kilonewton if the point x is less than or equal to 5 meters. And dy and Vc is equal to dy. There's no -1. If the load crosses the point D and goes to the sorry, wait. Yeah, when the load crosses the point C and goes to the other side, it's just dy. Now, if we find out what is dy when it is here, when x is equal to 0, what is dy? We found this. So at this point, the value is 7/5 minus 1, which is 2/5. So Muller-Breslau principle also says that it is to the same scale. So here it is 2/5. This is 2 meters. This is 3 meters. So by similar triangles, this should be 3/5 minus 3/5. And what will this be? What will this be? It is just jumping by 1, right? So here it is nothing but 2/5. This is 2 meters. This is also 2 meters. So by similar triangles, this should be minus 2/5. Now you see, where is the maximum shear force occurring? It is occurring when the load is right above the point C. So this is the ILD for VC. So here the maximum shear force of minus 3/5 is occurring. This is for a unit load. So for an applied load of 20 kilonewton, what is the value? It is minus 3/5 into 20. So 5, 4, 12. So it is minus 12 kilonewtons. So since it is a minus, the shearing at the point will be like this. Like this, opposite direction. So the answer is D. The answer is D. Now let's go to the next question. Now we are dealing with multiple loads, okay? So if a two load system of 100 kilonewton and 60 kilonewton, 20 kilonewton separated by 1 meter moves from left to right on the beam shown in question 7. So let us see this. Question 7 is this. Let me redraw the figure. So we have this is 2 meters, this is 2 meters. Between we have 5 meters. And the point E, as in the last question, is at 3 meters. So this is 3, 2, this is 2 meters, 3 meters, 2 meters, 3 meters. This is the point E, this is C, this is D. This is A and this is B. Now they're asking that two load system of 100 kilonewton and 20 kilonewton is moving. So first 20 kilonewton is going, then 100 kilonewton is going like this. It is moving from this side to this side. Wait, this is 2 meters. It's not 3 meters. 2 meters. Yeah, 2 meters. In this case, what is the maximum hogging bending moment at the point E? So for this, first we need to get the influence line diagram for bending moment at the point E. What it is, as usual, let us take the beam. So let me draw it to scale. This is 2 meters. This is 3 meters. At the point E, I have to release the moment. So let me put an internal hinge and apply the moment at the point E. Here I'm having the roller. So if I apply this, it is free to go up and down, but it is not free to develop a discontinuity. So this too again behaves as a seesaw. But it has to be connected at this point since we have not released the shear force like this. So again, the moment diagram will be something like this. How to find out the values? So as usual, let us apply at the point. So maximum, let us find out maximum moment will occur. This is positive, right? This is maximum positive. These are negatives. So maximum positive will occur when the load is here. Let us call this as 0.1, 0.2, and 0.3. So at 0.1, what is the moment value? It is 3, it is 2. So the reactions will be, the reaction coming here will be 0.4. The reaction coming here will be 0.6. I hope I know how to do it. And so what is the moment about this point? It is, take any of the two halves. So it's either 0.6 acting at 2 meters, which is 1.2. Or this side also you can take 3 acting at 0.4. So in any case, maximum is 1.2 kilonewton meters per 1 kilonewton load. Now let us take the point 2. So how does the point 2 look like? It looks like this. This is the case at point 2. So if I apply 1 kilonewton here, what is the moment coming on to this point? I have to find out. So let's draw the free body diagram. If we take moments about the point D, if we take moments about the point D, you'll get sigma md equal to 0, which means this will create a counterclockwise moment. So plus 1 into 2 plus, what is this? This is cy plus cy to 5 equal to 0. So cy is equal to minus 0.4 kilonewtons for 1 kilonewton. And if cy is so much, cy is minus, so this is acting downwards. And at this point, what is the shear force? Not shear force. What is the moment? You can take this half of the beam. So here you have cy acting downwards. So the moment that comes to the point E is minus 0.4 acting through how much distance? 2 meters, which is minus 0.8 kilonewton meter per kilonewton. So here the values minus 0.8 kilonewton meter per 1 kilonewton load. Now this is case 1, case 2, and case 3. Let us draw case 3 here. So this is the point E, this is the point C. You have a load here. Now again, let us do equilibrium. Sigma md equal to 0, which means that's a clockwise moment. So minus 1 into 5 plus 2, 7, right? 7 plus cy. into 5 equal to 0. So Cy is equal to 1 by 5 upwards. Now about the point D, if you take moments, about the point E, if you take moments, you will get ME is equal to 1 by 5 acting at 2 meters minus the actual load is acting at 2 plus 2, 4 meters. So 1 acting at 4 meters. 1 by 5 acting at 2 meters, minus 1 acting at 4 meters. So what is the answer? This is 2 by 5 minus 4, which is let me check this again. So if the load is acting at this point, you have
Cy is equal to
1
7.5, sir.
Cy is equal to 7. Sorry, yeah, this is 7 by 5. Correct. Thank you for the correction. I made a mistake. So 7 by 5 acting at 2 minus this. So this is 14 by 5 minus 4, which is 5 4 are 20. So it is minus 6 by 5. So at this point, it is minus 6 by 5, which is again minus 1.2. So fine. Now they're asking, now we have two loads acting one after the other. So how to find out the total bending moment? So if you know the influence line diagram, so what are the different cases that we can have? And they're asking the maximum hogging bending. So here actually, if you consider this, 20 Newton comes first and 100 kilonewton comes after that. So so let me draw the influence line diagram and then the cases. Suppose so what is the influence line diagram is something like this. Here it is minus 0.8. There it is 1.2. Here it is minus 1.2. So these two loads are moving like this. So first I have a 20 and then I have a 100. In this case, what will be the bending moment, maximum bending moment, not maximum bending moment. What will be the bending moment at this point, E? So in the first case, suppose this is case 1. In case 1, so let me take case and hogging, maximum hogging bending moment. So in case 1, if it is outside, only 20 will help. So 20 into 0.8, how much is that? So 116 minus 16. So in case 1, I'm getting 20 into 8 is 160 by 10. So it is minus 16. Now let's consider the second case. Okay. Now the second case, let me rub this. And let me move these. Let me move it this way. Right. So this is case 2. So this is case 2. In this case, how much is the value here? So they are separated by 1 meter. Yeah, they're separated by 1 meter. So this is 2 meters. So this is 1 meter and this is 1 meter. So here the value will be minus 0.4. So now what is the value here? It is 20 acting at 0.4 minus plus 100 acting at 0.8. The total moment. Okay, we're just superposing. So we'll get 20 into 0.4 is 8 and 100 into 0.8 is 80. So in the second case, we have minus 80 plus 8, which is minus 88 kilonewton meter. So I think there's a mistake in this question. I have tried it earlier. So minus 88 seems to be an answer. But we also have negative bending moment when you have the load on to the right side. So when we see that, let us see that when the load comes here, okay, let us see case 3. So in the negative part, if suppose we have this is case 3. In this case, what is the value? So we have 20 acting at 1.2 and 100 acting at minus 0.6. So this is 60. 20 into 1.2 is 24. So 60 plus 24. In case 3, we get minus 104 kilonewton. And suppose consider case 4 like this. And in case 4, suppose it is like this. In case 4, what do we have? In case 4, we have 100 acting at 1.2. So it is nothing but minus 120 kilonewton. So the maximum comes here when the smaller load has left the span and the larger load 100 is at just at the end. So this is the maximum. This is when we have a maximum bending moment at this point. So this needs to be corrected. That is also physically reasonable, right? Compared to this point, if you say, if it is like this, right? It will bend, in case 1, it will bend something like this. Something like this. And in this case, the load is closer to point E. So this will be the governing case. So here, all the options are wrong. So all options are wrong. If they're asking a maximum bending moment, it is minus 120 kilonewtons. Sorry everyone, unexpectedly my connection was off. The call dropped, the Teams meeting dropped unexpectedly. I didn't know why. Sorry, Ganesh,
Not at all.
can you repeat it? Now it was breaking. Can you repeat it? What you said?
Sorry. It's sorry.
No problem. Yeah, my call dropped unexpectedly. I have reconnected.
It's
Let me
okay.
proceed. Yeah.
Yeah.
Yeah. So the maximum actually is 120 kilonewton meters. So this is the correct option, but it is in none of the options. It is probably a mistake in last year's assignments. So yeah, so the right answer is 120 kilonewtons. Now let's go to the next question. Here they're asking what is the absolute maximum bending moment on the following beam due to three-wheel load shown below. Now again, here they're asking the absolute maximum. So absolute maximum means it could be in either hogging or sagging. But note that the given beam is simply supported. So the maximum will occur in sagging only. So this is one simplification. What is the other thing that we know? For a simply supported beam, now note that we can draw the influence line diagram, but ILD for bending moment at which point? Right? We can, if we know the point and the function that we want to find out, right? The bending moment at the point C, which is located at some distance from this support. If it is specified, then we can draw the influence line diagram. If that is not specified, in general, we cannot draw the influence line diagram. But let us use our intuition. So if this is a simply supported beam, so we'll get the maximum bending moment when the load is somewhere in the middle region, right? When these three loads are somewhere in the middle regions, we expect to get maximum bending moment. If it is somewhere close to the reaction support, it will not generate such high bending moment. So that is what we expect. So let us see if our intuition is correct. Okay. So let us consider one load at a time. So let us just consider a load of P acting on the beam at a distance y, or let's take x only. So this is at a distance x. This is L minus x. We know that in this case, the bending moment diagram is like this, with a maximum value of Px into L minus x by L. This is known. This, if you just resolve it, the force that comes on to here will be P into L minus x by L. Here the force will be P into x by L. If you take any half of the beam and find out the bending moment at this point, which is the maximum, you will get Px into L minus x by L. Now this is the maximum bending moment diagram for a unit load placed at a distance x. Now let us try when this maximum occurs. So m of x is Px into L minus x by L. This is the maximum, okay? M max of x. Now this maximum, when it becomes the maximum as a function of x, if we see, so dm max by dx equal to 0, which means you'll get P by L into L minus 2x equal to 0. So this will occur when x equal to L by 2, which means the load has to be placed at the middle for maximum bending moment. So now this is also supported mathematically. The ILD for bending moment at the point x equal to L by 2. Okay. So let us put this point C right here. Sorry. So let us put the point C here, right at the middle. This is C. Now let us draw ILD for bending moment at the point C, which is at L by 2. Simple. As usual, let us consider the beam. We'll use MB principle. Let us release the rotational restraint and apply the moment, sagging moment on the two parts of the beam, MC. Once we apply that, how does the beam deform? It deforms like this. So, according to the Muller-Breslau principle, the influence line diagram for the bending moment at the midpoint is like this. What is the maximum value? Maximum value is this, right? You place the load at the center, and what will be the maximum value? It will be 1. Here P is 1 into X is L by 2. L minus X is L by 2 by L. So it is nothing but L by 4, which is 7.5. So the span is 30 meters. In this problem, the span is 30 meters. So this is 7.5 meters. So this is the ILD for bending moment at the point C. Now let us consider all the different cases as we did. So since there are 3 loads, let us say in the first case, 80 kilonewton is at the center. In the second case, 60 kilonewton is at the center. And in the third case, 100 kilonewton is at the center. So let us consider 3 cases. So first case, $80 kilonewton is at the center. 60 is 2 meters away. So you see the question properly. We have this is 2 meters, this is 1 meter. 60 is 2 meters away, and 100 is 1 meter away. In this case, what will be the bending moments? Okay, so we have this. This is the ILD for the bending moment at midspan. The maximum is 7.5. So corresponding to the 60, that comes here. This is 2 meters. So what is the value here? This is 15 meters. In 15 meters, it is rising by 7.5. So in 2 meters, it will drop by 1. So here the value is 6.5. And at 100, the value is, so from here to here, it will drop by 1 because the slope of this line is 1 and 2. So here it will drop to 6. So this is case 1. So in case 1, what is the bending moment? In case 1, we get moment of, so in case 1, what do we get? We get 80 into 7.5 plus 60 into 6.5 plus 100 into 6. So that comes out to be 1590 kilonewtons meter. Now let us consider the second case. In the second case, let us put this 60 at the center. So the 60 is here, 80 is here at 2 meters, and 100 is here. So 60 is at 7.5. So 60 into, 60 into 7.5. 80, right? 80 is somewhere here, 2 meters away. So again, the slope is 1 and 2. So if you go 2 meters, it will drop by 1. So here it is 6.5. So plus 80 into 6.5 plus 100 into, where does 100 act? It acts midpoint of these two. And what is the value there? It is 7. Plus 100 into 7. How much is this? This is 1670 kilonewton meters. This is case 2. Now let us consider the third and the last case. Now 100 kilonewtons is at the center. So at the center we have 100 kilonewtons. At 1 meter from there we have 60 kilonewtons. And at 2 meters from there we have 80 kilonewtons. So 80 is at, so this is 1 meter from this, so this will be at 6. And this one is acting at halfway between 7.5 and 6.5, this will act at 7. And 100 is acting at the middle. So we get 100 into 7.5 plus 60 into 7 plus 80 into 6. So how much is that? We get 1650 kilonewtons meter. So out of these three, this is the maximum. So you see that although in this is the case where we have the maximum, the largest load at the center, it is not the case that generates the maximum bending moment. So this is the case where we have the minimum load at the center, but that is the case which generates the maximum bending moment out of these three. So the correct answer is this. So this is the correct answer is 1670 kilonewton meter. This is option A. Now let's go to the last question of the day. Choose the correct influence line diagram for the vertical reaction force at the point D of the following beam. So this is a very simple problem. Now that we have solved so many problems in influence line diagram, it's very simple. So what we should do, have an internal hinge. At the point D, you release the support and apply a vertical force of Dy. From there, we have this point E. And here, mid of these two, we have this internal hinge. And here we have the support. So this is B, E, F, D, C, and A. Now, very simple. How will this deform? So note that here we have not released any internal moment or the internal relative shear. So we have not released the internal relative displacement or the internal moment. So this unit will rotate as a rigid unit. So we have a hinge here. The region in between the hinge will rotate as a rigid unit, also obeying the other boundary conditions. So here, when we apply this, the deformed shape will be here. The displacement has to be 0. But there's an upward force. So this hinge can move up. So this hinge can move up, can go like this. And here the displacement has to be 0, definitely, because it's a support. We are not removing the support. So here it's 0, but it continues. It cannot change its shape because it's not an internal hinge. It continues as a straight line. And here there's an internal hinge, so the slope can change. So if you draw the influence line diagram, it will look something like this. Now, what are the magnitudes, right? So, okay, anyway, they're not asking the magnitude. So you see qualitatively, this is positive. This is the point D, which is at 2 meters. So it is here. Beyond D, up to the point E, it is positive. This is E, this is D, this is C, this is A. This is F, where you have the maximum, kind of maximum. This is negative, and this is P. So this is wrong. This is obviously wrong. You don't have a flat region. This is correct. This is correct. This is wrong. So the correct option is C. Now, so yes, we have done we have done all the problems for the day. If there are, as usual, I will upload the video and the problems in the folder. So I hope I have seen that in the course webpage, they have uploaded the link to the Excel sheet containing these worked out problems and the recorded videos. So in case, let me pause here. If there are any doubts, you can ask. If not, we'll close the session. Any doubts on what we discussed today? Yeah, I will wait for a couple of more minutes. If there are no doubts, then I can close the session. I'll wait for about 2 minutes. Then. Okay, everybody has left, so it seems that there are no doubts. So thank you everyone for attending this session. Let me stop sharing and let me stop the recording.